Hi students, last time we have recorded this lecture. In fact, unfortunately, uh, I could not unmute my system, so there were no audio. So this lecture I am going to re-record for you, and definitely this will cover the questions uh, which we be linking the first lecture series. The first lecture which we have covered, having some questions. I will just scroll down here just to have a look. What is NMR? We have discussed in the first lecture. Then we have discussed about that how many signals you will get in the following molecules. Then we have discussed about uh, like we drawn the structures and then we have wrote the number of signals for this. Then chemical shift we have discussed. What are the solvents used in NMR spectroscopy, integral height, shielding, deshielding we have discussed, factor affecting the chemical shift value. Then we have discussed about the what are the uh, if impact of the electron withdrawing group if it is attached to the same carbon having proton. Then how the distance matter in the change in the chemical shift value. And we have completed 10 questions in the first lecture. Now, this is the second lectures with audio. In fact, already we have recorded this lecture, but unfortunately, as I told you. So this is the most common questions in the university exam. What is magnetic anisotropy or anisotropy in NMR spectroscopy? In fact, when a pi electrons in the molecules like double bond, aromatic ring, or we can say the aldehydic group, if there is a pi electrons in the molecules nearby the proton which is under study. That means if we have the system like carbon having a proton and that proton is attached to the carbon with some aromatic system or maybe the olefinic double bond or maybe the carbon alcohol. So that means pi electrons nearby to the proton which is under actual study will have some extra field or extra induced magnetic field. In fact, what will happen, that induced extra magnetic field will push the proton in the same magnetic field in the same directions. In fact, like if the magnetic field is in the this direction, so induced magnetic field of this proton will be again in the same directions, and the induced magnetic field because of the pi electron, if it in the same direction, then what will happen, there is a push. As always I used to say the example, you are riding a cycle in the directions where there is a wind. Now there is a third force which is the friend which is pushing your cycle. That means you required very less amount of energy to go ahead. So that means, yeah, as I told you, the chemical shift or chemical del value is the ratio of frequency difference, that is a change in the frequency and instrumental frequency. That means applied magnetic field, or it may be the your radio frequency, because they are directly proportional. Now, in fact, when there is a push from pi electron cloud, that is induced magnetic field because of the ring current or maybe the pi electron current with the proton induced magnetic field, then what will happen? The required magnetic field will be less. If the required magnetic field will be less, the denominator will be less required. So that means if denominator is less, the del value will be mathematical equation will be high. So that means this magnetic anisotropy is directly affected the chemical shift value. Anisotropy means what? The normal induction of the field is promoted because of the external field or some nearby field. So the del value will be very, very high. So there are basic examples, that aromatic proton, aldehydic proton, olefinic proton, alkyne proton. So we'll see one by one. Here, this is a brief introduction about what exactly the magnetic anisotropy. Now, this magnetic anisotropy is nothing but change in chemical shift value because of some other fields. So there is a promotion of desilting effect. That means your uh, value or chemical shift will be higher in number. So that is we call it the downfield or desilted. Silted means some of the nuclei which will require more magnetic field, they are considered to be a silted one. But because of the magnetic anisotropy or diamagnetic anisotropy, we can say the required magnetic field will be less. So ultimately, the del value will be more. So this is what the magnetic anisotropy. If you read carefully, you will understand the meaning in simple language. I have explained it. You will understand very clearly. So let me move ahead with the examples. So I have already given the examples here. So this is the aromatic ring I have mentioned. So if you look at here in the aromatic ring, this ring current will induce some magnetic field. The proton to the so proton attached to the aromatic ring will also produce some magnetic field. So this applied magnetic field, the field induced by this ring current will be in the same directions, and there is a reinforcement. Reinforcement is leads to the change in the chemical shift value. That means the magnetic value, applied magnetic field required will be less, so the del value will be more. So in case of the olefin also exactly the same thing will happen. So the field produces by this double bond will be in the same directions to the proton as well as applied magnetic field. So the applied magnetic field and this proton, it reinforces, as well as to this reinforcement is extra. This is the cherry on the cake. That is the meaning of magnetic anisotropy. That means the field will be affected. So the circulation of the pi electron induce a magnetic field that adds to the applied magnetic field, which causes them experience a stronger net field and therefore resonate at higher frequency. Higher frequency means higher del value. So this is about the magnetic anisotropy context to the aromatic ring and olefinic compound. Let's see another example of magnetic anisotropy in context to the aldehyde. And let me get the pencil. Okay. So look at here again, the same example. Aromatic ring already we have discussed. Alkene also we have discussed. The chemical shift value you can see here in case of uh, let me get the pencil. Okay, so if you see here, the chemical shift value for aromatic ring is ranging from 6 to 9. For olefin, it is 4.5 to 6.5. Then carbonyl groups, like take the example of aldehyde, which will be in the range of 9 to 10. And then if the methyl group is attached to the aromatic ring, then it will be ranging from 2 to 2.5. That means these are the in fact change in the magnetic fields, required magnetic fields. Now there is a slight difference in case of triple bond. Now if you see here triple bond will have a sp hybridizations, whereas in case of double bond, the hybridization is sp2 hybridized, the structure is trigonal planar. In case of triple bond alkyne, the structure is linear, and the linear structure have freedom to move in the different directions. So there are two prominent directions, like linear will have parallel to the plane, perpendicular to the plane. So if you see here, the first structure, this one structure will have the reinforcement. This one particularly, the first structure will have a reinforcement, whereas the second structure will have the opposingly applied magnetic field. So in short, the one structure will reinforce the applied magnetic field, whereas the another one is oppose the applied magnetic field. And the net results of both will lower down the chemical shift value. If you see here, the chemical shift value for the alkynes will be 2 to 3, whereas the alkyne carbon is more electronegative as compared to the double bond. As double bond is sp2 hybridized, less S characters. But because of these two orientation, the net result is like one structure is reinforcement is helping to the that particularly example, as I told you, that one friend is pushing the cycle, but in case of another structure, another friend is pulling back the cycle. So energy will be required. So the net result will be the magnetic field required for the flipping of the nuclei will be less. One structure will less, the first one, and another one will be high. So both net effect will lower down the chemical shift value. And that lowering of the chemical shift value makes this magnetic anisotropy something different as compared to the olefin and the aldehyde as well as the aromatic ring. And here there is a change in the magnetic field in the fashion that there is a lesser uh, chemical shift value. That del value will be in the range of 2 to 3. More to the next example. What is spin-spin coupling? So spin-spin coupling already in case of magnetic anisotropy, we have discussed that there is a change in the chemical shift value because of the some field. Now here in case of spin-spin coupling, the proton which is under study, the nuclear which is under study for the flipping or in the process of resonance, magnetic resonance, that nuclear will have interference with the magnetic field of the nearby nuclei. Like you have a basic example, somebody has purchased some vehicle, the exact neighbor will always conflict, the boy or maybe the concerned person will fight for the same thing. Like, I should have that bike, I must purchase that bike. So that fight is because of the immediate interaction. So in the process of spin-spin coupling, the nuclei which are under study, they are having the similar effect. The nuclei which is nearby will interact, their spin interact with the nearby nuclei. So just let me take my pencil. So annotation has something problem here. So why the pencil is showing effect. Just a minute. Okay. Annotation. Okay. So just read out the first line of spin-spin or spin multiplicity. Spin-spin coupling refers to the interaction between nuclei, usually proton, that are chemically bonded or in close proximity. In this interaction causes splitting of the signals into multiples or multiplets, providing information about the neighboring group. So what exactly the mechanism for this splitting? The splitting mechanism is very simple. So just get this. Pen is not working. Pencil. So just a minute. Pencil is stuck somewhere. Note, annotation. Just give me a second. Just by the time you just go through this reading. Give me a second, so I will just stop the sharing and I'll again get back to you. Try. So exactly, some pencil problem is there, so I'm not able to draw the structures. So I just share this. All right. Hopefully this will work now. Yes, perfect. My pencil is back. So I'll scroll down the pages which we were talking. Now this is the question. Yeah, spin. Yeah, coupling and multiplicity. Spin multiplicity. Very interesting questions. Most of the time, university asks the questions, explain the multiplicity. Okay, what they ask, explain the multiplicity. Now, what will happen? What I said, if you have a system like this is a carbon having protons. Now, this is a proton, this is a proton. Now, if I am targeting to study this nuclei, this proton, like I irradiate this proton, as I told you the example, this person have purchased the bike. The exact neighbor, this fellow, will have conflict at their home. These are the two homes. कि मुझे भी ये बाइक चाहिए. ये इसने बाइक लिया तो ये भी बच्चा बोलता है कि मुझे भी बाइक चाहिए. So this splitting is what immediate effect. अगर नियर बाय दो तीन घर छोड़ के अगर है तो that effect will not be profound. So that means this nuclei, suppose this is a one nuclei having this spin. So this nuclei may have the opposite spin. So in short, what I can explain to you, look at here in case of this example. Now, if we have one proton, suppose nearby vicinity, the another example I would show here. This is CH3 and this is your CH. Now this is something attachment. Now my target is to study this CH3. Okay. Now another example is this CH3 and nearby there is a quaternary proton. Now to this nuclei there is nobody nearby. Nobody nearby in the sense a proton, which normally interact, their spin interact. So what will happen? So this proton interact with this proton. This proton do not have integral that spin nearby. So there is a first order equation called as n plus 1 rule. N plus 1 rule. Now we'll talk about this n plus 1 rule also. Now n is equal to neighboring proton. So how many neighboring protons are there? That many number of protons plus 1 will be the splitting line for that proton, which is understudy. Like take the example of this CH3, which is nearby no proton. No proton means n is equal to 0. So this will show you the only one line. That means we call as singlet. Now this CH3 is nearby one proton, 1 plus 1, 2 line spectra. So this 2 line spectra you will get for this molecule. So this is we call it as a doublet. So if there is a 3 line, means 3 protons, means 2 protons nearby. Like take this example, CH3 is nearby 2 protons. So there will be 3 lines. 3 lines means 2 plus 1, 3 lines. So this is we called as triplet. If there is a CH3 nearby, like take the example, this CH2 now is under study and it is nearby this 3 proton. So it will give you the 4 line spectra, like this is your quartet. This is we called as quartet. But how this n is equal to 0, 1, 2, 3 will give you the singlet, doublet, triplet, and quartet, and so on. Why it is possible? So that I can show you here. This is possible because of, like suppose take the example nearby, there is no proton. It's like the first condition. So no proton means there is only one proton. That one proton may have this spin or maybe this spin, clockwise or anti-clockwise. Now, if there are, like this is now singlet, this is for a singlet, single line. Now, if we have suppose two protons, means like one proton nearby, n plus 1. One proton means two line. Two line means that one proton can have the maximum possibility this way or this way. Now, this is the single proton. So you can just write only one. Okay, one. So this may be the clockwise or it may be the anti-clockwise. If there are two protons, so that two protons may be one clockwise, another anti-clockwise. Okay. Now you understand this is for n is equal to 0. N is equal to, okay, n is equal to 0. Now this is for n is equal to 1. Now let's see the n is equal to 2. 2 means two nuclei nearby. So these two nuclei will be both clockwise or both anti-clockwise, or it may be the one clockwise, another anti-clockwise, anti-clockwise, clockwise. That means you have maximum combination is 1 to 1. So this is the intensity ratio 1:2:1. So this will be triplet, and here the line intensity will be like middle line will be more because there are more spin combinations. So this way, this triplet line will have 1:2:1. That is, one middle line will be more, and triplet looks like this geometry. Doublet is what? 1:1, because this may be the clockwise or this may be the anti-clockwise. So this will be 1:1 intensity ratio. So the doublet will be like having the pattern is same height of the peak splitted. So this is for 0 proton, 1, 2, and 3. Let's see the 3, 1. Now here, this is the example I have mentioned here, the 3 protons. Now look here, 3 proton means like this is the example you can consider now. I'll take the pencil here. Okay. Now look here. Okay. Now I'll take this here. Now look at this example. This proton is under study, and this is near to this proton. There are 3 nuclei. So 3 nuclei will have 3 combination, means like 3 spin like this. 3 are all in a clockwise direction, or maybe all 3 are in anti-clockwise. In between combinations are these. One is anti-clockwise, both are clockwise, clockwise, anti-clockwise, clockwise, clockwise, both and anti-clockwise, and vice versa. So this way, the possibility is 1 and 3, 3, 1. So the intensity ratio is 1:3:1. So the peak appeared will be like this. Middle lines will be 3 times, and this is 1 time. So this is your quartet. So this way, the nuclei or a proton nearby will influence the proton which is studying, and that is we called as spin splitting or spin multiplicity. This is very important questions. Most of the time university will ask you the questions on this. Let's see now how it works. Like as I already mentioned to you, if one proton there is a singlet, so single line, 2 proton, 0 proton nearby. Like here, there is no proton. There is no proton, so single line. There is 1 proton, 2 line, that is doublet. The spacing distance is called as coupling constant, that we will discuss later. 2 protons, triplet, 3 protons, quartet, and their spacing distance is exactly same for this splitted peak. So this is quartet. So let's move on to the next. Now, first order spectrum for spin splitting. Now, how this n+1 has been originated. So that is the meaning of that. Now, this particular n+1 is simply from 2n I+1. So this is your I is equal to spin quantum number. Now, as I told you, proton NMR is active for half spin nuclei. So let's see the proton, C13, fluorine, phosphorus. Our interest is PMR, that is proton. So if I is equal to 1 half, so 2n half plus 1. So this 2 will get cancelled, remaining is 1 plus n+1. So this way, this n+ will initiated, and this is we called as first order equations. Now, how it is applicable? Like if there is a nearby CH2 in ethyl group, the CH3 will split into triplet because of the 2 neighboring group of proton. CH2 will splitted this CH2 because of this CH3 3 protons. So that is the quartet. In isopropyl group also there is a CH, and it is attached to the 2 methyl group which are equivalent. So there are 6 proton nearby to this. So 6 plus 1 septate, and that is 7 line spectra. And this CH3 both are same. So it is nearby 1 proton. So it will be a doublet. So this is a doublet. So this is what, how to explain this particular. Now this is Pascal triangle. Now this is interesting. As we go on adding one nuclei, the intensity ratio also goes on increasing for the spin coupling or spin multiplicity. Take the example, like no proton nearby, we said singlet will have no intensity ratio. If there are one proton, that is two peak, that is 1:1. Three means two nearby proton, so you will have 1:2, 2:1. Now how this Pascal triangle will initiate it? Add one and do the adding of this 1 and 2, so this will be 3. 2 plus 1, 3, 1. Now here, if I would write here 1, 1:1, now write 1, add 2 together and write 1. So this is this way. Now write 1, add 1 and 2, that is 3, 2 and 1, 3 and 1. Again, write 1, add 1 and 3, 4, 3 and 3, 6, 3 and 1, 4, and write 1. And this way you can go on adding and adding. You will get the exact intensity ratio as you goes on increasing the number of protons. So this is what we call as the Pascal triangle. So you can practice, you can play with this, you will enjoy the intensity ratio. Now, the most important part of the university questions, they will give you the structure and they will ask you write the spin multiplicity, or they will ask you the questions, write the number of signals and write the spin multiplicity or spin splitting. Like take the example of ethanol. Now ethanol structure, some point they may give the structure and they may not give the structure some point. So you have to draw the structure. Ethanol, this is structure. How many different types of protons? There are three. 1, 2, 3 types. So 3 signals. Now this CH3 is nearby 2 protons. So this will be 2 plus 1. So this will be triplet. Now look at here CH2 under study, which is nearby 3 protons. So this OH is not included in the spin coupling. The reason behind OH, NH2, they have the active proton. They always exchange with the impurity. And because of the exchange ability, they could not coupled. And that's why the coupling is not possible. They appear itself as a broad singlet. Whereas CH2 is nearby 3 protons, so it will be quartet. So for ethanol, you will have triplet. This is your triplet, quartet, and broad singlet. So these are the 3 peaks. Now integral height of CH3 will be more. This peak will be more heighted. This will be less, and this broad signal. So this way you can calculate the integral height too. So the point is here, question is here, write the splitting pattern and number of signals. Or I not mention here number of signals, but you can write the number of signals too. So there are 3 peaks, triplet, quartet, and broad singlet. Okay. Now, some point they may ask you to write the chemical shift value too for such types of proton. So the CS3 is alkyl group attached to the alkyl. So it will be in the range of 0.9. CH2, which is attached to the O, this chemical shift value may ranges into the range of 3.5 to 4.5. OH is notorious. It will ranging from 1 to 5 ppm. So this chemical shift value is also important, ppm. Okay. So this is what the splitting pattern for ethanol. Like methanol, CH3OH. Now, how many signals? This is nearby 0 proton. So this will be singlet as well as this will be singlet. The del value for this will be maybe 4 and this will be maybe 5. So this way, this is singlet, singlet. Like draw the structure for ethyl methyl ketone. What is ethyl methyl ketone? This is CH3, CH2, C double bond O, CH3. Now this is ethyl methyl ketone. How many different types of protons are there? 1, 2, 3. This CH3 and this CH3 is not same. So there are 3 signals. Now, what is the multiplicity for this? Write the multiplicity. So this is nearby 2 proton. So 2 proton means triplet for this. How many protons nearby? There are 3. So this should be a quartet. And how many for this? There is no. So this is a singlet. So this way you can easily write down the splitting pattern for the ethyl methyl ketone. So write the coupling, their chemical shift value, del value. So this will be 0.9. This is attached to the carbonyl group, ranges from 2 to 2.5. So you can write down 2.2 or maybe 2.3, and you can write here 2.1. So this way you can write the chemical shift value too. Come to the next. Okay. Next is your ethanol, ethyl methyl ketone. Now let's have the propanol. Now propanol structure. So number of times propanol and propanol you get confused. Propanol means alcohol. So this is your one propanol. So I'll write the structure CH3, CH2, CH2, OH. Okay. This is your 2-propanol. So I'll write later on. So how many signals you will get? 4 signals you will get. Splitting pattern. This will be triplet. This will be singlet. These are the 2 easy way. Now the middle one. So this is nearby 3 proton to this side, 2 protons to this side. So you can write the multiplet straight away. But that multiplet, if you want to superfine, so this will give you the quartet first, and this will give you the triplet first. So you can write the quartet of triplet. So this is nearby 2 protons to this, not the OH counted. So this will be triplet. So you can write the multiplet or quartet of triplet and triplet for this. What is the chemical shift value? This will be 0.9, no doubt. This will be a little bit higher. It may be 1.2, and this is attached to the O. So it will be 4.2, 4.1, 4.5. And this is your ranging from 1 to 5. So you can write down 5 there. So this is how the chemical shift value and number of signals for the propanol. Now 2-propanol. So this 2-propanol is having the symmetry. Symmetry means this CH3 and this CH3 will have exactly same field. So this will be referred as AA. So you will have one signal for both, but the integral height will be more for that number of proton. So this proton is nearby 1 proton. So this will be doublet, but this proton is nearby 3 plus 3, 6. 6 plus 1, septet. Septet. Okay. Septet is for the CH. This is your singlet. Okay. So this way you can easily write down the splitting pattern, or you can write down septet as a multiplet also. Okay. Chemical shift value, this will be 0.9. This middle one is attached to the O. It will be 4.2, 4.3, and this O will be 5, or maybe the 4.5. So that depends. So this is all about propanol to propanol. Let's move on to the next now. Propanol. Now null means aldehyde. So this is CH3, CH2, CHO. So these are 3 carbon atoms. 1, 2, 3 carbon atoms. So 3 signals you will get. Propanol will get how many signals? 4 signals. Even 2-propanol you will get the 3 signals. 3, 4, and 3. Now splitting pattern. This will be triplet. Now this is nearby 3 proton, and this is 1 proton. This proton is in the same field. It can coordinate. It is not exchangeable. Aldehyde proton never exchange. So this can be written as a like quartet of doublet, or you can write straight away multiplet. This is nearby 2 protons. 2 plus 1 means triplet. So the chemical shift value, this will be 0.9. It will be attached to the carbonyl group. So it is 2.3, 2.5, and this is 9.5 for the aldehyde proton. So this way, propanol chemical shift value, their splitting pattern, and number of signals can be written. Let's move on to the next. Okay, propanol is done. Now let's see the butanol, butanol. So always get confusion, butanol and butanol. Butanol means aldehyde again, CH3, CH2, CH2, CHO. So this is the structure of butanol. How many signals you will get? 4 signals you will get. 4 different types of protons are there. Now, what else you can do here? Now, triplet for this. Now, this is quartet of triplet. That means straight away multiplet. This is triplet of triplet. You can write down multiplet, and this is your triplet. Chemical shift value, this will be 0.9. This will be 1.2. This will be attached to the carbonyl group. So 2.3, and this is 9.5. That is aldehyde. So this is for your propanol. Now propanol. So CH2, CH2, OH. how many signals you will get? 4 signals, because 4 different types of protons are there. Now splitting pattern, this will be triplet, sorry, triplet for the CH2, this will be quartet of triplet, this will be triplet, and this will be singlet. Chemical shift value 0.9, 1.2, attached to the O, that is 4.2, this will be 5, and this is all about butanol. This is your butanol. Let's see the another example. N means straight chain. Propyl bromide, that is CH3, CH2, CH2, Br. So this is N-propyl bromide. How many signals you will get? 3 signals, because 3 different types of protons are there. So this will be referred as the triplet. This is a quartet for this and triplet for this, or in short, you can write down the multiplet, and this is triplet. So you will have 3 signals like this. Chemical shift value 0.9 for this, 1.2. This is attached to the Br, maybe the 3 or maybe 2.9 or 2.8. So this way, and propyl bromide will show the splitting pattern. Move on to the next. Next is your isopropanol. Okay, isopropanol structure is like there is a 2-propanol. This can be written as a 2-propanol. Already we have discussed this example, propanol. So this is 3 signals you will get. Iso or 2 is same. You will get 3 signals. This is for doublet for this, because this is same, and this is your septate 7-line, and this is singlet. Chemical shift also we have discussed. You can just have the look at the first example. Now look at the methyl benzene. This is also called as toluene. So the toluene structure is here. Now how many signals you will get? For methyl 1, this proton, and this proton. These are the different. Now this and this is same. This and this is same, and this is different. So 1, 2, 3, 4. So total 1, 2, 3, and 4. 4 signals you will get for methyl benzene. But how to see the splitting pattern? This is very interesting one for the benzene ring. So I'll draw again the structure for splitting pattern. Now this CH3 is nearby no proton, because this is a quaternary. So there is no proton. So this will be singlet. Now this proton, and this proton. Now A, B, C. So this is also A, this is also B. So this is same. So this is nearby 1 proton. So this will be N+1. So this will be doublet. Now this B will be coupling with the A as well as C. So this will be doublet of doublet 2D, D. And this C is nearby this B and this A. So this is nearby this B and B. So there are 1 + 1, 2. So this is nearby 2 protons. So this will be triplet. So for the splitting pattern, this is singlet, this is doublet, this is doublet of doublet, this is DD, and this is T, triplet. So this is 4 signals for the benzene. So any aromatic ring, if it is there, the splitting pattern will be exactly same. Doublet, doublet of doublet, triplet. Monosubstituted ring, I am saying. Okay, so this is all about toluene or methyl benzene. Like, let's have another example. Ethyl methyl ether. Already this is same exactly for the ethyl methyl ketone. So this is CH3, CH2O, CH3. So this will be triplet, this will be quartet, this will be singlet, 3 signals, 0.9. And this is attached to the O, it will be 4.5, this will be 4.2 or 4.3. In case of aromatic ring, I have not mentioned about the chemical shift value. So I can mention here. So the methyl group attached to the aromatic ring will be having 2.3 to 2.5 del value. And this proton this proton and this proton. So this will be having like 7.3, this will be 7.2, this will be like 7.1. In the similar range, 1 or 2 units will be here or there. So you can look at the exact chemical shift value in the book. You will get the idea about that. Now let's see the another example of xylenes. There are 3 different xylenes. So I'll write here the structure. So this is your paraxylene. There is a metaxylene. There is a there is a orthoxylene. Okay, so this is CH3, this is your CH3. Now look at here. In paraxylene, you will have symmetry. In case of metaxylene, there is a symmetry. In case of orthoxylene, there is symmetry. So you have to take half of the peak in count. Now here, this proton is same. Exactly this and this is same. So this one peak and another peak. Okay. So this will be singlet, this will be singlet. Now this proton do not couple each other because they have exactly same. They are exactly same. They are having exact environment. So they never ever split. So the proton which are having exact similar environment, they do not split. Like take the example. This is CH2, this is CH2, and attached to the Cl and attached to the Cl. Just for the example of having similar field. If I put a plane here, this is also A, this is also A, because attached to the Cl, Cl. So this will not show you the triplet. You cannot write triplet for this or triplet for this. So this is simply you have to write singlet. You will get only one peak, singlet. So they will not couple to each other. So they are having exactly same environment. So same environment peaks do not couple. That is the meaning of this. So let's move on to the our xylene stuff first. Okay, now look at here. So how many peaks you will get for the xylene? You will get only two signals. That is two peaks. Both are singlet and singlet. This is singlet. This is singlet. So this is all about your xylene of paraxylene. Metaxylene now I'll talk about. So I'll rub this because I want a proper space. So this is done. Now let's have a metaxylene. Now this methyl group do not have any proton. So this one and this one is same. So you refer as A. This is your B. This is your C, and this is your D. So this is C again, and this is your same. So how many peaks you will get? A1, B2, C3, and D4. So 4 peaks you will get. The splitting pattern you can write down. The CS3 will be singlet, no doubt. This B is nearby only the quaternary proton, so there is no proton, so singlet. This C is nearby D, so this is a doublet, and this D is nearby C, so this is a doublet. So you will have doublet for this, methyl is singlet, this proton is singlet, and this is exactly the same. So total 4 peaks. 4 peaks includes 2 singlets and 2 doublet. So this is for the meta. Ortho will have also the symmetry. So this is A, this is your B, this is your B, this is your C, this is your C. Symmetry is there. So this will be singlet. So this will couple with this, no doubt. This will be having you are splitting as a doublet, and this will be having, this will couple back to this. They will never couple to this, so this will be doublet for this. Now look at here. In case of particularly meta, we have done something wrong here. So I will redraw the structure and I tell you, because it was a messy though a little bit. Look at here. So in case of ortho, how many peaks you will get? This methyl is singlet, this proton is doublet, this proton is doublet. So there are 3 peaks. Okay. Now in case of this, there are proton here, 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 and this one. Now A, suppose this is B, this is C, C, and E. I have rearranged it differently. So this is singlet, this is singlet, this is singlet. Now this C is coupled with D. Okay. So I would say D. But this D is nearby 2C. So that was the little bit change. So this is a triplet. I mentioned here doublet. No, this is a triplet because it is nearby 2 protons which are equivalent. So this C and C, the 2 protons. So this will be triplet. Okay, so this is a slight difference between the meta. So hope you understand this. Let's move on to the next structure is ethyl methyl ketone. So rest of the structures are very simple. Ethyl methyl ketone. So this is CH3, CH2. Okay, just a minute. Ethyl methyl ketone. No, ethyl acetate. So this is something ester group, C double bond O, CH2, CH3. How to draw the structure? Structure is already drawn. So this is singlet. So this is quartet. This is your triplet. This chemical shift value, you can just work it out. Now for the acetophenone structure is ketone. So this is your acetophenone. This is your singlet. Now for the aromatic ring, as I told you, this proton, and these are the proton. So this is a doublet, this is double DD, and this is your T triplet. So this is for aromatic ring. Most interesting is your vinyl chloride, that is CH2CHCl. By looking at direct structure, you can see this one group and this another group. But when you have such structure, you have to do the expansion or the structural form like cis and trans, like this. And then you have to look into that this Cl is nearby to this proton, this is cis to this is trans to this is geminal to this. So that means this A, B, and C, all three protons are different. These two protons are not same. So you will have three signals. Each signals will couple with both the remaining two protons. So that means how it can be written, so that I can show you here. So I will just clean the mess a little bit here. Now look how to draw the splitting pattern. As I told you now, these are some of the different pattern A, B, C. So this will couple with this and this will couple with this. So that means this will be doublet of doublet. This B is again coupled with this A and C. So this will be again doublet of doublet. This C will couple with this B as well as A. So this will be again doublet of doublet. So vinyl group will show you doublet of doublet pattern. Doublet of doublet means what exactly? It is simply like you have this doublet, but this doublet further split into the doublet. So this is we call as doublet of doublet. That means these two line will have, this is a doublet and this is a doublet. This is a pattern, that is doublet of doublet. That is multiplicity. Let's move on to the next. So here, what structure left now? I'll scroll down this page. Vinyl chloride is already we have discussed. Let's see this this structure and this structure. This is CH3CH, and this is a dibromo. That is 1,1. On the same carbon, there will be bromide, whereas there is a 2 bromide, but they are separated apart as a 1,2. So in this case, there is a symmetry for the structure. So this will be A, this will be A. So you will get singlet for all protons. So only one line. Whereas in this case, A and B, both the groups of protons are different. So this will be doublet and this will be quartet. So this is mostly the choice of the examiner, this 1,2,1,1 dibromo type of compound, vinyl chloride. So never ever miss this particular splitting pattern. So this is all about the spin splitting or spin multiplicity, which is very interesting. Do the practice and definitely you will get the questions out of this. Move on to the next questions. What is coupling constant? Or explain it with the suitable example. Now, coupling constant is nothing but it's a constant. We always know the constant is the fixed number. Now, what fixed number? I'll let you know. Now, suppose we have a group called as CH3, CH2. Now, these two groups of proton, two different groups of proton, they join together. Now, when they split, like this will split as a triplet. That means the triplet will be like this, as I told you. So this is a triplet for this. And this will split a quartet for 3 protons. So these quartets will be like this. Just understand. Okay. Now, this distance, this spacing distance is fixed. Now, what is coupling constant? The spacing distance between the splitted peak. Now, this is a triplet, this is a quartet. Now, this spacing distance and this spacing distance is suppose J. J is equal to what? J is equal to the number. and 3J means the bond between these, like this carbon and this carbon having a proton like this. So how many bonds are in between? So if I would say this nuclei couples with this nucleus, so there is a one bond, two bond, three bond. So I refer as a J is equal to J3. J3 means in between these two nuclei there are three bonds. So the spacing distance is called as the coupling constant, which is a constant number. Now this is a constant number. Now if I would say 7 hertz for this, so it will be exactly 7 hertz. That means this particular triplet and quartet, they are having a coupling. They attach together. That is what we call as coupling constant, and it is a fixed number. For cis, trans, vicinal, geminal, that numbers are fixed. When we identify that number, the equal numbers, we can say these two groups are having a coupling together. So what exactly this coupling constant? Just we'll read a couple of lines. When two nuclei are close enough, usually 2 to 3 chemical bonds, as I told you. So these are the nuclei, very close. So the bond between like two also, some point two bonds also. So two bonds, if it is there, like geminal one. Now this is two bond. Okay, one, two, one, two, three. So this is J3 and this is J2. So that is usually two or three chemical bond apart. Their magnetic field influence each other because this magnetic field and this magnetic field, or this H and this H magnetic field influence each other, and this interaction causes signal to split. We know that this proton will takes n+1 rule and split as a doublet, suppose if it is not attached something here, and this will also doublet. So the spacing distance between this is nothing but the coupling constant. So the interaction causes NMR to split rather than a single line. The distance between the splitted peak is called as coupling constant. जैसे कि this doublet will split this spacing distance, and this doublet spacing distance is nothing but the coupling constant, which is a constant fixed number. So if you read now, you will understand what is coupling constant. Now for the cis and trans, now this is a great application in NMR spectroscopy. You can easily distinguish between a cis and trans geometry of the proton. Now suppose we have here cis geometry, their coupling constant will be ranging lesser than the trans one. So you can easily distinguish between the cis and trans, and this become one of the application in NMR spectroscopy to identify cis and trans isomers. Let's move on to the next. What is D2O exchange? So this D2O exchange is nothing but the simplification of NMR spectra. You know that already I have mentioned the OH group is having a notorious activity. In fact, it has a tendency to exchange with the acidic impurity or impurity, we can say. So that's why this peak is ranging from 1 to 5. Then in the scale 1 to 5, it is not easy to locate. So the spectrum becomes complicated. Some point it is a hump type of peak, like a broad siglet. So to identify such active proton containing species like OH, NH2, amide, or acid, we need to treat them with D2O, and that D2O, deuterium, is inactive in NMR, proton NMR spectroscopy. And when we record the NMR, the normal NMR suppose, and we have some of the peaks which are having multiple peaks, and that we are confused with which one is which, or particularly which one belongs to the proton. To identify that proton, when we re-record the spectrum with D2O, same sample, when we are filled with the NMR sample with the solvent, and we put some few drops of D2O like this, few drops. Then when we shake it, the proton of the OH will replace with the deuterium, and the OH peak in the first spectrum will be missing. So suppose if I redraw the spectrum, I will find that this peak will be missing, and that missing peak will be the OH. So this way we can easily track the position of the active protons like OH, NH2, or amide by using the D2O exchange. And this most of the time in NMR combined problem, they will say, oh, the one proton broad singlet exchange with D2O. That means that proton may be the OH or NH2 depending on the molecular formula. So this is the application of D2O exchange. Let's move on to the very important topic of combined problem. Now, combined problems. So let me just look at the time. So I'll solve a couple of problems, and then we will re-record another lecture also for the remaining one. Now, what is combined problem? Combined problem is like having the information of two or more spectroscopy technique. Now here in this problem, we have targeted only two spectroscopies. So two spectroscopy techniques already we have given, like IR, PMR, and rest of the things. Maybe like some point they may give you the UV, mass, depending on. But as we have focused on IR and PMR, so let's have the information about the IR, NMR, and how to assemble the structure. That all details we are going to talk in the next lecture, because we have more than 20 combined problems and their solution too. So all the lecture, all the problems, the combined problems, we will discuss, and their answers will be given. And this will be a very crucial problem. Most of the universities papers I have uh, check, and their use problems, their ask problems I have noted down here, and their solutions will be given. So this is very long lecture now. I will stop here, and I will re-record after some time the another lecture on combined problem. It may be extended to one or more our time. So I need to take a break. So don't miss this another lecture which is based on combined problem. For the upcoming lectures, like I'm going to record some of the lectures on organic chemistry stuffs also, IR spectroscopy also, some basic, maybe the carbohydrate, then stereochemistry, which are purely asked in TYBSc examinations. So in couple of days, I will record maybe the series of lectures on organic chemistry. So don't miss these lectures. Whenever, like I most of the time I post the link on the teachers group, some point you may miss it. So if you subscribe this channel, definitely will get the notification, and you can get the new lecture series at all in the one stage. So don't miss this lecture series. In maybe the couple of days you will get all the organic uh, problems which are asked in the university, their solution, and their discussions on this lecture. So with this, I'll stop this lecture over here. Thank you very much indeed.